Okay, this is the second half of lecture 5.5. This is about limiting and excess reagents. Okay, so we're going to look at limiting and excess reagent problems. Those are generally stoichiometry problems, just like the ones we did in the previous part of section 5.5, except for in those cases, we only had amounts given for one of the reactants. Okay, in this case, we've got amounts given for multiple, usually two, of the reactants. And so in order to get to the right answer, you have to consider both of those bits of data instead of just one. Okay, and so there are going to be a couple of, sort of a couple of extra steps, I guess. But the plan really is basically very similar. I will mention that the way this is taught sometimes in high school and even in some college classes can be very confusing, and some people get really mixed up on this. And I've talked to people who are literally brought to tears trying to solve limiting and excess reagent problems. But the good news is the reason for that is because they were taught in a way that is just completely ludicrous. The way to do it is actually really, really simple. And that's based on the chocolate chip cookie principle, which I will show you in a few minutes. And if you can understand that, you'll have no problem with that. In the process of working through this problem, we'll talk about limiting and excess reagents and applications. We'll do one problem. They're a little bit long, so we'll do one problem of this, and that will show you how it works. And we'll also touch on the idea of theoretical yield and percent yield. Okay, so here's a typical sample question. We've got a reaction here, iron reacting with hydrochloric acid to make iron chloride and hydrogen, and we've got 15 grams of the iron, and we've got 25 grams of the hydrochloric acid. Okay. And like I said previously, we had problems that would say something like, how much iron chloride can you make using 15 grams of iron, right? Or how much iron chloride could you make if you have 25 grams of hydrochloric acid? And those were pretty straightforward. Here, instead, we have to consider both of those at the same time. So that makes this a little bit different. And this is how you can, if you're working these problems, this is how you can recognize a limiting and excess reagent problem. And that's what this is. We'll write that down. All right, and we'll talk about what that means. Okay. All right, now the way we're going to solve this is by applying what I like to call the chocolate chip cookie principle. And this is just a really simple framework through which you can view one of these problems. Okay, so let's look at this similar problem. According to the recipe shown here, and here's a recipe. It's a fake recipe, by the way, so don't try to make cookies with this. They'll be awful. According to the recipe shown here, how many batches of chocolate chip cookies can Dave make using the current contents of his fridge and pantry? And let's say he goes and looks in the fridge and the pantry, and this is what he finds. Okay. All right, take a look at this for a few minutes and see if you can figure out how many batches of cookie Dave can make. And then I'll join you with my answer. Okay, so when you look at this, you can look at each ingredient independently and say if one batch of cookies requires 2 eggs and he has 12 eggs, then that means he has enough eggs to make 6 batches. Okay. Each batch of cookies requires 2 sticks of butter, and he's got 4 sticks of butter. That's twice as much as he needs. So that means he has enough butter to make 2 batches of cookies. Each batch requires 1 cup of flour, and he has 8. So he has enough flour to make 8 batches. He has, following the same reasoning, he has enough sugar to make 6 batches. But each batch requires a bag of chocolate chips, and he only has 1 bag of chocolate chips. So he only has enough chocolate chips to make 1 batch of cookies. Okay. So given all of that, how many cookies can he make? Right? Well, obviously, the answer is he can only make 1 batch of cookies, because once he mixes everything together to make 1 batch, he runs out of chocolate chip cookies and he can't bake anymore. Okay, so the amount that he can make is 1 batch. Okay, all right, and this is these cookies, or excuse me, the chocolate chips here are the thing that's going to run out first as he's trying to make batches of cookies. And as soon as he runs out of chocolate chips, he can't make anymore. So the chocolate chips we would say are limiting, because they limit how many batches he can make. Okay. And here we might say that's a limiting ingredient. When we have the same phenomenon in a chemical reaction, we call it a limiting reagent. And all of these things over here, he has more than he needs. So for these, we say they're excess. And again, for this, we might say there's excess ingredients. In a chemical reaction, we call that an excess reagent. Okay. All right. So the idea is, in this case, there are what, 5 different ingredients. Usually, we'll just have 2 or 3 ingredients in a chemical reaction. The idea is you just look for whichever one runs out first. That one is said to be limiting, and that's going to determine the total amount of reactant that you can make. Okay. All right. So let's go ahead and apply that to a chemistry problem. Okay. So here's our sample question. We've got iron and hydrochloric acid, 15 grams of iron, 25 grams of hydrochloric acid, and we want to know how much iron chloride we can make. Okay. So what we're going to do is we're going to do here the same thing that you probably did mentally when you were looking at the chocolate chips. You probably didn't write everything out, you just kind of looked at it and came to a conclusion. But here we're going to do that a little bit more systematically. Okay, so for a problem like this, make a plan. Okay, and first thing we're going to do, we don't know which is the limiting reagent yet, but we'll just assume that the iron is the limiting reagent. Okay, and based on that, we'll answer the question, how much iron chloride can we make? Now, sorry for the handwriting there. Iron might be the limiting reagent and it might not. We don't know that yet. Okay, but what we're going to do is we're just going to assume that iron is limiting and figure out how much iron chloride we can make. Okay, then we'll take the next reagent. Then we'll do the same thing with the hydrochloric acid. We'll assume that the hydrochloric acid is the limiting reagent. And then we'll ask the question, how much iron chloride can we make? We'll solve that problem. Okay, and then just like with the chocolate chips, whichever of those two whichever of those produces the least amount of product is actually the limiting reagent. So we start by assuming that each one is the limiting reagent and seeing how much we can produce. And then, after we've done that for both of them, this is super important, whichever one of them produces the least amount, that's the limiting reagent. Okay? And this is also really important, whichever one produces the least amount, that's how much you're going to make. A lot of people work through this. They get an answer based on this assumption, they get an answer based on this assumption, and then they sometimes have a tendency to add those two together. Okay, that's not how it works. Okay, whichever one produces the least, that's the limiting reagent, and that determines how much you're going to make. Because as soon as you make that amount of reactant, that limiting reactant, as soon as you make that amount of product, the limiting reagent runs out and the reaction stops. Okay, so the amount that you're actually going to produce is always based only on the limiting reagent, not on the pair of reagents. Okay. All right. So let's see how this works on the next problem, next page. Let's take a look. All right. I moved this up a little bit so we have a little bit more room. All right. First, we want to figure out, we're going to assume that the iron is limiting, right? So we want to solve this problem. 15 grams of iron produce how much iron chloride? Okay. All right. And then this problem is going to be just like the ones we did in the first part of 5.5, right? We're going to ignore the hydrochloric acid completely, and just based on this 15 grams, how much iron chloride can we make? All right. Since we're trying to relate iron and iron chloride, we know that we have to have a mole to mole conversion in the middle. That's always going to be true. Okay. And that relationship comes from the balanced equation. So 2 moles of iron is equal to 2 moles of iron chloride. All right. Then we also have to do a gram to mole conversion here. We can get that from the molar mass. Right? 1 mole of iron. And for this, since it's an element instead of a compound, we can just look directly on the periodic table. All right. And then we have to do the same thing over here, converting from moles to grams. And again, we showed how to do this a while back in a previous video. All right, so we got that. Okay, so those are the 3 different conversions that we need. Okay, I'm going to go ahead and erase these numbers down here because I need room to work, but I hope you have written them down. Okay. All right. All right, so our first step is to convert from grams to moles. Then we need to do this conversion between moles of iron and moles of iron chloride. And again, these the 2's here come from that balanced equation. And then finally converting from moles of iron chloride to mass of iron chloride. We use that, use the molar mass. And we'll check to make sure that all of our units cancel. Grams of iron cancel. Moles of iron cancels. Moles of iron chloride cancels. And we're left with 43.563 grams of iron chloride. Okay. All right. We'll need to look at significant figures when we do that, but we don't need to worry about that yet because we don't even know if that's the right answer yet. We need to go back and do the same thing with the hydrochloric acid. Okay, so what I would have you do, actually, before we do that, let me mention one thing. If you map out your plan here, okay, so now we're assuming that hydrochloric acid is the limiting reagent. Okay, in the middle here, again, you're always going to have a mole to mole conversion. Okay, so write in that mole to mole conversion here. Then I'll write it in as well. Handwriting's not great, sorry about that. But in the middle, we're going to need a mole to mole conversion between moles of hydrochloric acid and moles of iron chloride. So we're going to be using this and this. So if we write that out as an equation, we would say, we would say 6. My pad is messing up a little bit, excuse me. 6 moles of HCl is equal to 2 moles of iron chloride. Okay, just wanted to point that out because last time we had a 2-to-2 ratio, now we've got a 6-to-2 ratio. So I just wanted to make sure we're all on board with that. Okay, now that you've got that, go ahead and calculate the molar mass of hydrochloric acid. You'll need that. And do the same thing that we did. Step 1 was assume that iron is limiting. Figure out how much you can make with the iron. And then step 2 is assume hydrochloric acid is limiting. See how much you can make with the hydrochloric acid. I'm going to erase this. And while I erase this, why don't you work on that second part. Take the 25 grams of hydrochloric acid and see how much iron chloride you can make. And then I'll write my calculation down and you can check yours and mine. Okay, so I've written that plan up here. Right, we're going to assume that hydrochloric acid is limiting, and we're going to figure out how many grams of iron chloride we can make with that. So I'm going to convert from grams of hydrochloric acid to moles of hydrochloric acid. Then I'll convert from moles of hydrochloric acid to moles of iron chloride. And then finally from moles of iron chloride to grams of iron chloride. All right. So I've set now that I've got my plan, I've set up my calculation. I'm going to check, as I always do, check to make sure that my units cancel out. Then last, moles of iron chloride canceling out so that our final result is grams of iron chloride. And when I do that, I get 37.073 grams of iron chloride. Okay, I hope you got the same thing. Again, we'll need to modify the significant figures when we get to the very end, but this is our tentative result for this part of the calculation. Okay, all right, let me clean this up and we'll answer the final question. We'll get to the end of this. All right. Okay, so what we found was that our 15 grams of iron was enough to make 43.563 grams of iron chloride, and our 25 grams of hydrochloric acid was enough to make 37.073 grams of iron chloride. Okay, so what that means is that this reaction is going to keep chugging along. We'll make 10 grams of iron chloride, make 20 grams of iron chloride. We'll keep reacting to make 30 grams of iron chloride, 35 grams of iron chloride. And then once we get to 37.073 grams of iron chloride, that's as much as we can make with the hydrochloric acid. We don't have enough hydrochloric acid to go any further, so the reaction stops at that point. Okay, so that means means a couple things. One, it means that the hydrochloric acid, actually I'm not sure I love that blue. Means that the hydrochloric acid is our limiting reagent, and it means that the iron is our excess reagent. Okay. It also means, and extremely importantly, that the amount of iron chloride that we can make is this amount and not that amount, and not the sum of the two. It's just this one, because again, once we've made 37 grams, we run out of hydrochloric acid and the reaction stops. Okay, all right, so this is our correct answer. Now we can go back and look at significant figures. If you go back and look at your calculations, you'll see that we've got 4 significant figures in most of the calculations, in most of the conversion factors. Remember, those mole to mole conversions are counting numbers, so those have an infinite number of significant figures. So the sig figs here are controlled by the data that was given to us at the beginning, and that is this 15 grams and the 25 grams, which have 3 significant figures. So we need to round this to 3 significant figures. So our final result is 37.1 grams. All right, that's our final answer on that problem. Okay, when you have one like that, again, the plan is take the first reagent, assume that it's the limiting reagent, even though you don't know whether it is or not. Figure out how much product you can make. Then take the second reagent, assume that it's the limiting reagent, see how much product you can make. Whichever one of those gives you the least amount of product, that's the limiting reagent, and that's how much you can make. Okay, it's really pretty simple. You got to do a lot of calculations because you have to kind of do it twice, but conceptually, it's actually pretty simple. Okay, and in these questions, you'll often also be asked to identify the limiting reagent and the excess reagent. So you want to know those terms. Okay. All right. And there's one more thing that often happens in these limiting and excess reagent problems. Although I guess you could do this You could see this as a follow-up question in one of the earlier types. Uh, Very often asked about the percent yield of a reaction. And this is an important concept. When you do a reaction, you want to make sure that you get a good yield. You want to be efficient and try to get as much out of it as possible. And so a percent yield is a good way of assessing how successful a reaction is. Okay, and so in order to calculate a percent yield, we need to actually talk about three kinds of yields. There are three different things that are important here. The theoretical yield is the amount that you're expected to produce based on that stoichiometry. So that means that the balanced equations and the amounts of reactants that you started with and all of the mathematical relationships before them, that gives you a theoretical maximum amount of product, and that's your theoretical yield. Okay. The actual yield, this is pretty simple. The actual yield is just the amount of product actually produced. And a reaction might not produce as much product as you expect. Sometimes because the reaction just doesn't go to completion. There are some things that cause chemical reactions to not progress as far as you would have expected. But also this incorporates things like losing a little bit of product on your filter paper, or some product getting sloshed out of the beaker, or anything that happens in the lab that causes you to lose a little bit of your product or to be slightly inefficient. Okay. All right. And then the percent yield, which is what you're usually asked to calculate in these problems, is just a comparison of the actual yield and the theoretical yield. So the percent yield is just the actual yield relative to the theoretical yield. Okay. So it's just the actual yield divided by the theoretical yield. And then in order to make that a percent, that should give you a decimal number. And then to convert that to a percent, we'll just multiply by 100%. Okay. All right. So let's try that with this problem here. Okay. All right, so in this problem, the theoretical yield, that's what we calculated on the previous page, right? Our theoretical yield was 37.1 grams. The actual yield, that's what's given to us here in the problem, is 32.3 grams. Okay, so our percent yield is just the actual divided by the theoretical yield. Okay. And notice whenever you're calculating a percent, your units should always cancel. If your units don't cancel, you're probably doing something wrong. Okay. All right, so those cancel out and multiply by 100%, and I got 87.126%. Again, we should look at significant figures. We've got 3 sig figs in both of these values here. So we want to round this to 87.1%. That's our theoretical yield. All right. When you're calculating a theoretical yield, most reactions do pretty well. There are some reactions that are where the product is so valuable that you could do a reaction where you only get a 10 or 20% yield and it's still worthwhile because you want that product so much that you can even afford to use a reaction that's not very efficient. But most reactions have pretty good efficiency, and so theoretical yields are often in the 60, 70, 80, maybe 90% ballpark. Okay, not always, but usually. The reason I mention that is if you're doing a problem on a homework problem or an exam problem or a study problem, whatever, and you calculate the percent yield, if you get a 3.2% yield, you probably have a mistake somewhere. That would be pretty unusual. It's not impossible, but it would be pretty unusual. So I would go back and check your math, particularly on an exam. If you get a very low yield, 5, 6%, even 12 or 13%, there's a good chance that there's a mistake in there. Another thing that is a clue that you've got a mistake is if you get a percent yield that's greater than 100%, then you almost certainly have a mistake. There's really no way in reality that you can get a percent yield greater than 100%. Sometimes in the lab, you can get a percent yield over 100% if you have some measurement errors or if your product is a little bit wet, and when you weigh it, you're actually weighing a little bit of water with it. So in those cases, sometimes you'll get a percent yield of 102 or 103% or something like that if you have a little bit of error. But generally speaking, you shouldn't have a percent yield over 100%. And on a homework or exam question, I can't imagine a situation in which you'd have a percent yield over 100%. If you ever see that, you almost certainly made a mistake. I can't imagine any way that wouldn't be a mistake. So go back and check your math. All right, so that's it for limiting and excess reagent problems. So the method for solving these is based on that chocolate chip cookie principle. If you can understand the little problem that we did with Dave trying to make chocolate chip cookies, whatever ingredient runs out first, that limits your product, whatever you're trying to make, whether it's cookies or iron chloride or carbon dioxide or whatever runs out first, that is the limiting ingredient or the limiting reagent, and that determines the amount that you're going to produce. Okay, that thing that runs out first is it's called the limiting reagent, right? And anything else is an excess reagent, the things that produce more than you would need. And then we just did a calculation on theoretical yield and percent yield. And remember that percent yield is the actual yield divided by the theoretical yield. And then in order to make that into percent, we'll multiply by 100%. All right, this is a really important topic, so please practice these. You should definitely do several of these until you feel really comfortable with them. Once they get so easy that you feel like you got it right before you even check the answer, then you can go ahead and stop. But until you get to that point, you should keep practicing these because they're very, very important. All right. Thank you for sticking with me through this, and I will see you in the next one.